You know how you can just tell how strong a cup of tea is by its color? Well, today, we're going to break down the science that takes that exact idea and turns it into an incredibly precise tool for measuring, well, pretty much anything in a solution.
Okay, so here's what we've got on tap. We'll start with that basic idea of color. Then, we'll get into the language of light itself. After that, we'll look at the rules of absorption. They're simpler than you think. We'll take a tour inside the machine that does all the work. And finally, we'll check out what happens when the rules, well, when they don't quite work.
All right, first up, we're starting with something you already get, probably without even thinking about it. The darker a liquid is, the more stuff is dissolved in it. We're about to see how scientists took that simple observation and built a super precise instrument around it.
I mean, you just know, right? You glance at a cup of tea and you can tell if it's going to be a strong brew or just colored water. It's something we do every day, but that simple observation, that is the absolute core principle behind a seriously powerful scientific tool.
So this whole idea, it has a fancy name, colorimetry, but the principle is exactly as simple as it sounds. The more intense the color, the higher the concentration of the substance making that color. It's a direct relationship, something we can actually measure.
And you know, our ability to measure this stuff has come a long, long way. Back in the day, scientists literally just used their eyes. It was called visual colorimetry. They'd hold up a sample next to a bunch of known standards and just compare. But our eyes can be tricked, right? So we moved on, we replaced the human eye with a much more reliable photoelectric cell. That gave us the photometer. And now we're in the age of the spectrophotometer. This thing is so precise it can measure light we can't even see, all the way from ultraviolet to infrared.
Okay, so to really nail down this connection between color and concentration, we need to speak the language of light. And really, it all boils down to two key ideas: absorbance and transmittance.
So picture this. You've got a beam of light, right? It's got a certain brightness and it's heading straight for our sample. As it passes through that colored liquid, the molecules inside are like tiny little sponges. They soak up some of that light. The light that actually makes it through to the other side, that's what we're going to measure.
So, the light that actually gets through, we call that transmittance. It's basically just a percentage of the original light that survived the trip. If half the light makes it out, the transmittance is 50%. Super simple.
But what's often way more interesting to scientists is the light that didn't make it. That's called absorbance. It tells us exactly how much light got soaked up by the solution. Now here's where things get really clever. We use a logarithm to calculate absorbance. And you might be asking, why? Well, it's because while transmittance gives you a curve when you plot it against concentration, absorbance gives you a perfect, beautiful straight line. And a straight line makes all the math so much easier. So we know that absorbance and concentration are connected. But how exactly? Well, the answer comes from two incredibly simple, almost common sense laws that, when you put them together, form the entire backbone of this technique.
First up is Lambert's law. And honestly, this is just common sense. The farther light has to travel through something, the more of it is going to get absorbed. It's exactly why it's way harder to see the bottom of a deep lake than it is to see the bottom of a shallow puddle. The distance, the path length, it matters.
And second, we have Beer's law. This one is also super intuitive. It goes right back to our cup of tea. The more concentrated the solution, the more tea molecules you have floating around in there, the more light they're going to absorb. Makes sense, right? The solution just looks darker. And when we smash these two simple laws together, we get the really elegant Beer-Lambert law. The equation is straightforward. Absorbance equals the concentration times the path length times this special constant. Now that constant, that's like a unique fingerprint for every substance. It describes how strongly it absorbs a specific color of light. And just like that, with one clean equation, we can figure out the exact concentration of something just by seeing how much light it soaks up. Okay, so we've got the theory, we've got the equation. Now let's actually go inside the machine that makes it all happen. We're going to follow a single little beam of light on its journey through a spectrophotometer. All right, here's the play-by-play. It all starts with a source of light. Think of a simple light bulb. That light gets focused, and then bam, it hits a prism, which splits it into a full rainbow. Then, a tiny little slit acts like a bouncer at a club, only letting one very specific color, one single wavelength, get through. This pure one-color beam then shoots through our sample. And finally, a detector on the other side measures what's left of that light and turns it into a signal we can read.
Now, the real heart of this whole machine is a part called the monochromator. You can basically think of it as an incredibly precise filter. Its one and only job is to pick out one specific color of light from that whole rainbow, and this step is absolutely crucial. Why? Because that Beer-Lambert law we talked about only works if we're using a single, pure wavelength of light.
So here you can see how it all fits together. The diagram on the left gives you the big picture, the light's complete path from the bulb all the way to the detector. And then the image on the right zooms way in on that super important monochromator, showing you exactly how that prism and the slit work together to isolate the one perfect color we need to get a good measurement.
Now, as awesome and powerful as this technique is, it's not perfect. The Beer-Lambert law, it has its limits. So let's take a look at the situations where the rules start to bend a little and what other tools scientists have in their toolbox for when that happens.
Okay, so the biggest limitation? Concentration. That Beer-Lambert law is fantastic for dilute or weak solutions, but once you get them too concentrated, the molecules start bumping into each other and interfering, and that beautiful straight line relationship we rely on, it just falls apart. Other things like changes in temperature or pH can also throw a wrench in the works, sometimes by actually changing the shape of the molecules we're trying to measure.
So when measuring the light that gets absorbed isn't going to work, scientists can just flip the script entirely. They use a technique called flame photometry, and the principle here is the complete opposite. Instead of looking at the light that gets soaked up, we literally burn the sample and measure the unique light that it gives off.
And here's how that works. The sample gets sucked into a really hot flame, and that energy gets the atoms all excited. When they get excited, they start to glow, and each element glows with its own unique signature color. It's like a chemical fingerprint. It's basically like turning the atoms into millions of tiny colored light bulbs. The brighter they all glow together, the more of that element you've got.
So you see, from something as simple as judging a cup of tea, to analyzing a medical sample, or even figuring out what distant stars are made of, it all comes down to this fundamental dance between light and matter. It gives us a way to see what's otherwise totally invisible. And it really leaves you wondering, right? What other invisible stories are all around us, just waiting for us to shine the right kind of light on them?